like normally would be in a lecture theater. Normally I would be able to talk to people sort of face to face, but it's a great delight to be able to talk to the society. And as after the kind introduction, I'm Péter Juhász. I'm a DPhil student in the department here, and today I'm going to be talking about ultracold atoms. And subtitle reads Many Body Quantum Physics with the cooler stuff in the universe, which seems quite an interesting subtitle, but I'm going to jump on it in a minute. What does it mean actually? And just one thing I would like to say, which would be easier in sort of normal times, that if you have any questions in the meantime, please don't hesitate to ask. I'm going to ask the moderators and the committee and whoever to sort of like raise the questions and like ask people to sort of speak up, unmute themselves, whatnot. If anything comes in the chat, also please feel free to read it out. I'm very happy to answer them on the go. Otherwise, there will be time set up for questions and answers afterwards, so it should be fine. All right. Okay, so let's get cracking. So first of all, it's just a sort of like a brief outline of the talk and what I'm going to be talking about today. The first sort of like point will be ultracold. How old is ultracold? What does it mean to be ultracold? And what do we do here in the first place? Second point will be how do we get so cold and why do we want to get so cold? Like why is it an interesting thing to do? And third point will be the how. So how do we do that? How do we get so cold? And the last bit will be some actual science in the sense, okay, then we have what we have, and then what do we want to do with it, and what can we do with it? Okay, so first of all, let's talk about temperature scales, just to get everyone on board. So this is the normal centigrade scale that everyone is aware. And because this talk is addressed to Physics Society talk, I would hope that I wouldn't need to explain that we can go from a linear scale into a logarithmic scale, and then from centigrades to kelvins. 0 Kelvin is just the absolute zero that we can achieve. It's about minus 273 centigrades. And on the right hand side, you see that is basically I've just made it into a logarithmic plot. So let's talk about temperature scales in a logarithmic fashion. And on the left hand side, I will say how cold it is. Something that I'm talking about on the right hand side will be how fast it is. And so ordinarily in the lecture theater, in like a room, it's about 20 centigrade, so it's like 300 kelvins or so. That means that atoms move at about 300 miles per hour, which is about as quick as like airplanes go, essentially. So if we go hotter than that, the center of the sun is say like a million Kelvin or so, or a bit more. And at that speed, atoms move at about a speed of a rocket launching, essentially. So what we are talking about is cold. So let's explore the other end of the scale, where everything would expect that, okay, well, surely the coldest things that we have in the universe is outer space, and that's about right in the sense that it's about the background radiation is 2.7 kelvins. And the coldest thing in the universe, except our physics laboratories, I'm just going to explain in a minute, is this Boomerang Nebula here. So this is about 1 Kelvin, which is 1.5 kelvins colder than the background radiation. So it's an interesting phenomena going on there, that something is colder than like even outer space. And that temperature atoms move at about 30 miles an hour, small car. But what we are doing in our labs with ultracold atoms is sort of this scale, okay? So this is less than a microkelvin in the nanokelvins regime. So it can be between 1 nanokelvin to a couple of hundreds of nanokelvin. And at this speed, atoms are only moving with like sort of 3 meters per hour, which is about as fast as a snail goes. So that's when we are talking about ultracold atoms, we mean that we are sort of 6 orders of magnitude or even more orders of magnitude colder than outer space, which is a quite an interesting and big achievement. So that's how the cooler things in the universe, as in the coldest things in the universe, are in physics labs. All right, so that's basically it. And then what can we do with all this low temperature physics? And just a brief overview of the history of all this. The first sort of like breakthrough, like one of the big results in the early 1900s, was the liquefaction of helium. And then we discovered the superconductivity, and then also we came up with BEC theory. This is what I'm going to be talking about later. BEC stands for Bose-Einstein condensation, and I'm going to explain what this means in a minute. And then we also sort of, did experiments with superfluidity of helium. We came up with the theory of superconductivity and high temperature superconductivity. And then sort of like almost, or like exactly 70 years later, then we had the theory of the Bose-Einstein condensates by, well, Bose and Einstein. We managed to actually make BECs in the labs in 1995. Good. So just a couple of words, just a single slide on the basic tenets of quantum physics in general. And that's just to reassure those who are non-physicists, which is sort of 1/3 in the audience, I can see. So what is quantum physics, just for everyone who's not physicist? Like, quantum physics is just basically the physics of the smallest scales, if you like, okay? So smallest scales, small energies, low temperatures, and we're just interested in like how things work at that small scales, essentially. And this is all, this was one of the pioneers of all this was this guy, Erwin Schrödinger, who was, by the way, a fellow of Magdalen College. It reads that on his Wikipedia page that he wasn't quite successful at Oxford because of his unconventional domestic arrangements when he wanted to live with 2 women at the same time. So he was kicked out pretty much and had to go away. But anyway, he developed his famous Schrödinger equation. And that's one of the things that governs this area of physics, if you like. And one of the few interesting things is that both energy and momentum and all these kinds of observable things are quantized, as in like restricted to discrete values. So you cannot have like a continuous energy varying from 0 to whatever, but you have some sort of like finite states that you can step in between, okay? Another thing is wave-particle duality, that we can think about particles as being waves at the same time, and they can express different kinds of behavior depending on circumstances. Also, the other quite interesting thing about quantum physics, and one of the basic things about quantum physics is the uncertainty principle, which just says that, okay, however, you cannot arbitrarily precisely measure anything or like different things at the same time. And it's not because if your equipment is not correct or not perfect or whatever, it's just something which is quite intrinsic to how our world works, is that we can't know everything at the same time, if you like. But also, this all works at macroscopic scales as well. There is nothing preventing us for using it at large energy scales, except, you could be asking then, okay, when I walk into a room, why do I not behave like a wave and sort of like diffract off from a door? And that's just because there are these high energies involved. So all these effects are quite minor, and you wouldn't be able to see this in an everyday environment. Okay, so then just going back to wave-particle duality, but let's just sort of like compare these. So like these ways we can think about stuff in general is that, well, either something is a particle, which has like some size, some finite size d, and it goes with some velocity v. So there is like a momentum associated with it, and it just goes in some random direction. Or you could think about something as like being a wave. And just like water waves or whatever. And it was this guy Louis de Broglie who said that, well, the two things are, well, you can go from one thing to another, and everything which has some momentum, then you can associate a wavelength with it. And the two things are, well, not really different, but it's sort of like the same kind of things, which was a really, really unsettling thing to do, because you would expect that these are two remarkably different ways of thinking about something, and it's just it's either one or the other. It's not that like it can be two things at the same time. So okay, so what did humanity do? We set up experiments to figure out. So, well, it was first J.J. Thomson who says that, like, okay, I've just discovered this new particle, and the electron is a particle, and he got the Nobel Prize for it. But well, maybe to his bad luck, he had the sun was also very good, and then he figured out that it's a wave. So and his son also got a Nobel Prize for the exact opposite, or if you like, if you just sort of like confirming that things can either be a particle and a wave at the same time. So basically, what governs if something is a particle or a wave is that how the physical size of the particle, which we can think about in some ways, is how does it compare to the wavelength associated with it? And if something has a bigger wavelength than how big it is, then it's more like a wave. If the wavelength is much smaller than how big it is, then it's more like a particle. The reason we behave like particles and we don't behave like waves is because our momentum is very big, because our mass is very big compared to atoms, and so this wavelength is very small. So like the wavelength is much smaller than our actual size. So that's why we are not sort of like diffracting off doors and that sort of things. Okay, then let's then think about this a little bit more. So basically, why is it interesting, or like why do we need to get so cold? So that's sort of like the second point in the talk, is that we want to get this wavelength quite big, at least bigger than the distance between the particles, in this case, or the size of the particles, to be able to see quantum physics in action, if you like. So what we do is that, okay, we have some gas, and then like in a classical limit, these are just like particles, like marble balls bumping off each other, and it's the classical things that that the wavelength doesn't really matter, and we just think about these as being marble balls, if you like. And as we as we cool something down, at first we sort of like enter this wave mechanics regime, when things start to behave like a little bit like waves, and then you enter this wave mechanics. But if you make it even colder, and say the wavelength is now bigger than the distance between the particles, what will happen is that their waves are sort of overlapping each other, and this is something by the Bose-Einstein condensation, of course. This is called Bose-Einstein condensation. So essentially, you need to slow things down enough so that their wavelength is big enough, so that they overlap and they go into sort of like a single macroscopic quantum state. This is a quite interesting thing, and this is quite a big thing, because then what that means is that, well, you have a system which is sort of like in a classical size, in the sense that these Bose-Einstein condensates can be sort of like viewed under a microscope, if you like, and this is something which is still not nanometers or fractions of nanometers, but something relatively big. You have many atoms, people make condensates of millions of atoms, but they all are just a single quantum system, and they all interact with each other, and they are just all described by a single wave function, rather than everyone's going whichever they like. So the way science put it is this: when this was first achieved in 1995, they basically say that, okay, so the individual atoms are sort of like lined up to each other, if you like, and they like all sort of like make one wave function, and you can describe like how they go with one wave function, and there are these like hotter particles around. So this was the cover of science. Okay, but okay, that's one thing to sort of like figure this out theoretically, and it was done by Bose and Einstein in 1925. But it's another thing to actually make this, precisely because you need to cool things down. And say, just as a summary, ultracold atoms are okay. So what they mean is that this wavelength is larger than the distance, the interparticle distance. They move at sort of millimeters per second, and they are sort of few hundred nanokelvins cold, or maybe even colder than that. The whole thing just becomes a macroscopic quantum system. And these three guys managed to actually make this happen in 1995. They all got the Nobel Prize for it. And this is probably the most famous picture ever taken of Bose-Einstein condensates. What you see here is that this is basically the momentum distribution of your atoms. And what you see is that, like, as you make it gradually colder, so sort of like temperature decreases this way, you see this like large peak coming in, developing in the middle. So essentially, that means that, okay, you have lots of atoms which are about at a zero momentum state. So that means that they are very slow. They are all interlocked into one big Bose-Einstein condensate, if you like. Okay, so then how do we all do this? And this is the way we get so cold is with laser cooling. People would expect that, okay, well, lasers, I know what they do with lasers. One thing is that they can like cut, whatever. We all see Star Wars, and like they are cutting each other's in half and whatnot. But like taking this quote from Goldfinger, it would have been like, Bond asking the X-Mag need to burn, and Goldfinger would say that, like, no, Mr. Bond, I expect you to freeze. And I realize I'm taking a double digression here, but as I was browsing the Wikipedia page to find this picture for Goldfinger, I figured that I'm sure that not many of you know that, like, how Goldfinger was named. It was quite interesting because apparently there was an architect who built a not very nice looking building in the neighborhood of Ian Fleming, and he so hated the building that he named the villain Goldfinger, which is the name of the architect as well. So this is the building that he built, and he was just so not up for it that he actually made him the villain of his next book. Anyway, let's get back to physics. So let's get back to laser cooling and how can we do this? So the way we do laser cooling is, well, you can think of photons. Like light is made up of sort of like light particles, if you like, and this is something that we call photons. And the way you actually cool the atoms down is that, okay, you know, atoms fly one way and you fly light particles the other way, and they just sort of like bump off each other, and like and then that way the atoms would slow down. Sort of like thinking about, you know, how effective is that? Okay, like shining light on something and then like, you know, expecting something to slow down, as if you're, you know, someone would be skateboarding towards you and like shining a laser pointer, and you would suddenly expect that like it will stop him. This is basically, you know, a good analogy is that like, okay, you fly essentially tennis balls against a tank, and your tank is the atom, the tennis balls are the photons, and this is sort of like how many photons you need to be able to actually like stop a tank, if you like. So, you know, if you fly, you know, many balls like in an amount of time, then you can get sort of like 100 microkelvin regime, or even colder, sort of like 10 microkelvin regime, and that can, you know, cool things down quite a bit. And just thinking a bit more about how this works, actually, well, what you essentially need to consider is that, okay, you cannot fly any kind of photon or anything, because like otherwise, you know, everything would just freeze in light. Like, how does this actually work? But the way it works is that, okay, but atoms can actually absorb light on some like discrete energy levels, right? Which is just basically the energy associated with an atomic transition. You know, like an electron goes from one energy level to another energy level, and then that point, you know, the photon can be absorbed. So what happens is that, okay, well, your atom flies to the left in this slide, your light comes from the right, and then basically this photon gets absorbed by the atom, but then it gets emitted, of course, but in a random direction. So what that means is that, okay, well, I fly these photons from one way and they get emitted in a random direction. So you essentially, like the net effect that happens is that you slow down your atom in that direction. It's an also interesting thing to think about, you know, was this sort of like the limiting factor for this process? Like, why does it only cool stuff down to sort of like a microkelvin regime? Why can we not go colder? Because that's still, you know, orders of magnitude bigger than what we need for this Bose-Einstein condensation to happen. And that's precisely because of this process. Because if you think about it, you know, what happens is that, you know, you basically absorb one photon, but you emit that photon. So when you're like at that, you know, when you're at that code, that it's sort of like it's basically, you know, the energy associated with the recoil of the atom by it emitting the photon that it just absorbed. So that's why it cannot get any colder, essentially. And as I said, you know, you cannot use any type of light, as in like any wavelength of light. So if you make this blue light a bit green or like a bit red, it won't absorb it that well. Okay, so you actually need to get your light wavelength very precisely at the atomic transition. And then how do we actually, you know, use this to trap atoms and then to sort of like cool atoms? Is that what we do it is a really smart thing, also earned the Nobel Prize for someone, is that we use red detuned light. Okay, so this atom would absorb blue light, but we actually use green light, which it wouldn't absorb. Except if the atoms, you know, in the lab frame, this is what we have, but in the atom frame, because of the Doppler shift, well, if the atom goes this way, then from the atom's perspective, or like from the atom's frame, this light or this photon would be blue, so we'll be on the atomic transition, whereas this would be even more red than it was before, so only this one will be absorbed and not that one on the left. So that means that the atom will always, you know, absorb from the direction that it is going. So what you can then do is that if you basically shine light on your atom from every single direction, you can like cool it down in the sense that you can slow it down, because it will always absorb from the direction it is going to. And as I said, there are two great physicists involved in this who got the Nobel Prize for this. So that's sort of like the first part of cooling. But as I've said, okay, this is very good. We can go to sort of microkelvins regime, but it's still like factor of like 100 too high than what we need to do. So the next thing is this 1 milliamp pound coffee machine that I mentioned at the very beginning, and that's literally using, you know, the same kind of effect that you would do to cool your coffee, in the sense that, okay, well, I have two hot atoms in a trap. Then what do? I say essentially just, lower the trap in the sense that I just let the hottest atoms sort of fly away, and I just like constantly blow away, if you like, or like let the atoms escape, which are the hottest, and then only the cool atoms will remain. Okay, so that's quite good, because then basically you can like lower your temperature to as low as you like. On the other hand, and that's the sort of drawback of this process, is that you lose atoms in the meantime, right? Because you need to essentially lower your trap so that you let the hottest atoms escape, which is great because you have something colder, but equally you lose a lot of atoms in this process. So you need to sort of like get your atom levels and atom numbers high up so that like what remains is sufficiently cold, yes, but it's also sufficiently many that you can actually study and explore. And as I've said, there is no theoretical limit that we know of this process. So the coldest thing ever achieved is half a nanokelvin. That was done by Wolfgang Ketterle in MIT. Also shared the Nobel Prize with the other two guys who achieved the BEC in 1995. Okay, finally, how do we trap atoms? So that's one more thing. Well, because we've managed to then cool them down, but it's just one thing. The other thing is that we need to still trap them. And one of the things that we can do is an optical dipole trap, so optical trapping. So this is kind of a two-step process, if you like. First of all, you shine some light on your atoms, and then sort of like in a semi-classical way, you could say that there is a dipole induced by that electric field. But then what happens is that, okay, you have a dipole induced in your atom, but the dipole interacts with the electric field which induced it in the first place. So that will mean that, okay, this interaction will have some interaction energy associated with it. And if you choose your wavelengths well, then you can make it sort of being attracted to light in the sense that this interaction energy will be negative, and therefore you will be able to keep your atoms in place. So basically, what you say is that, okay, so your dipole potential, or like this interaction potential, is proportional to your intensity. So you basically have like a Gaussian, light beam. Then that will mean that you will have a Gaussian trapping potential, and then your atoms will all fall down in the middle of the beam, so the brightest spot in the beam. This was developed by Claude Cohen-Tanucci, also won a Nobel Prize in this. I'm luckily in a place where every single person I mentioned got a Nobel Prize for what they did. So that's a nice field to be in. Final component is then how do we sort of like take pictures, or like what do we do to actually like look at data? And it is simple enough in the sense that we just literally sort of like take pictures of the atoms that we use. So we shine the lights that we used for slowing, for example, and precisely because they are resonant and they absorb some of this light, we can just basically look at the shadow of the atoms. So you have some atoms, you have your light, some of these atoms, or like all of these atoms, will absorb some of this light and therefore will cast a shadow. And then you have a good enough camera which can sort of like discriminate between this shadow and will be able to see the atoms. And you can do multiple things. You can sort of like look at in situ, so like sort of like when the atoms are still in the trap, and that will give you an idea about how your atoms are distributed. So like what's their number density as a function of position. You can also do time of flight. So essentially, you just like release the atoms from the trap, and then this is sort of like t varies this way, and you see that the atoms are just sort of like falling down. They're also expanding, and this is the key thing that you want to look at. You want to basically see like how the number density is distributed as a function of your momentum. And that's another piece of information. This way you can get an information about their energy distribution. The last thing that you can also do is to interfere different parts of your cloud, and that way you will be able to get phase information of your trap. Now, some of you can maybe recall that this is actually just an experiment. It's like a very expensive experiment to measure G as well, in a not very precise way, by the way. But this is something that we can do, something which can be done for sort of like a rough calibration of your experiment. So that's something that we can do. But this is how we get our data essentially. And then basically the question is then, okay, this is all fine, but what do we want to do with this, or why do we want to look at this? And this is all because of this many body effects. Say the sort of like a classical example is 15 geese flying in the sky is not the same as like 15 times a single goose flying. they take up this sort of V shape because it is energetically favorable for them to fly in this shape, because they can like sort of like cancel air friction or like optimize air friction in this way. So that will be the easiest for them to fly in this way. So if you have sort of more than one atom, or you have like multiple atoms and they interact with each other, that is more interesting or somehow fundamentally different than having single atoms and looking at them. So that's what we want to look at. And this sort of like many body physics or many body effects is something that you can see all over the world and all over the place. This is what happens with superconductivity, as I mentioned at the beginning. Sort of like you can also look at turbulence. This chip should say quantum computing. So this is something that we would that also sort of take advantage of this. But also in the financial markets, if you have lots of sort of shares going up and down, I think simple example is that all shares go up. That means that aeroplane shares go down because oil is expensive and they need kerosene to fly. So there are many body effects everywhere in the world. Good. Also, now the things that we want to, but what's also the reason for looking at many body of these ultracold atoms and not sort of say like take another system? And so let's just plot this out in sort of like a length scale veil. And what we say is that, okay, well, we can look at individual atoms, but they are like very, very small. So, well, we could look at the nuclei of the atoms, but they are too small and it's hard to observe them and hard to measure them. Well, we could look at sort of like very big things as like neutron stars and whatnot. They have lots of neutrons all interacting, so that would be great, but they are very far, so that's not great. Then there is this sort of like more sort of everyday sort of life scale or length scales, like yes, like superconductors and superfluid or helium and whatnot. But this is just like sort of plain hard to do. So the way we choose this is because the ultracold atoms are relatively simple to start off, and they're also highly tunable. So you can do lots of different things. You can choose your atoms to say that whether they are bosons or fermions. You can choose your interactions and tune the interactions. You can tune the trapping geometry and what else you want. So so that means that they are very, very they are very sort of a good and tunable and accessible system to do quantum physics. And so one of the advantages of all this is well, you can do something called the quantum simulation, because essentially it's hard to simulate materials because they require lots of computation power, if you like, and it's you cannot simulate systems in more than say 100 atoms or whatever if you want to do it sort of like infinitely precisely. But what you can do is that you can engineer a system which has the same kind of interactions and has the same kind of geometry, and then sort of like fill it up with your ultracold atoms and then measure it. So that way you can really, really simulate like how an equation works, or like how a system works that you have a model for. And this was coined by Richard Feynman. This is something which lots of groups are working towards, to simulate different kind of condensed matter systems and these kinds of things. What else can we do with this? Well, there are lots of cool things that you can do. So as I said, that one of the things that you can do is that you get the information form is interfering different parts of your cloud. So on the left hand side, in this sort of like figure A, if you like, this is just basically a single BEC, but it is trapped in sort of like in a double potential, as in like you have one BEC here on the left hand side, which is fairly big, and you have a smaller proportion on the right hand side. What then you do is that like, okay, you switch off all these laser beams that they are holding these in place, and then just like let them sort of like overlap in this time of flight and see what happens. And what you see is that we have these fringes. So this is experimental data on the left-hand side. On B and C is the simulated data. And you can see this sort of matter wave interference. It is in my opinion, it is a really, really interesting and a really sort of like convincing way of looking at of testing quantum mechanics, because you are all used to interfering water waves and like interfering waves, but you're literally interfering electrons here, which and you see that this is like a 70 micron cloud. It's like big enough. I think it's definitely bigger than I think hair, for example. And you interfere it, and you have this sort of like interference pattern. So I think this is actually amazing. But you can also look at is also quantized vortices. So basically, just start to stir your BEC. And then you see all this nice sort of shape emerging. So all these holes that you see here are vortices, and they're all very nicely aligned. And the reason for this is because basically it's just like a very, very highly excited state of your Bose-Einstein condensate. So of course they will have some sort of geometry to it. You can also arrange them in optical lattices. See, as I said, that like we can change the geometry of how we trap them. So we can trap them in a sort of like a lattice structure. So like rather than having them as a bulk, as in here, we can also put them in a lattice, and this can be used for quantum simulation of simulating some condensed matter system. But then also the other thing that you can do is tune interactions. And so going on to talk about the interactions then, and then sort of leading slowly onwards of what we do here in Oxford in my group, is we are looking at atoms which come with two kinds of interactions. One is just simple contact interactions, which is a bit like, it's just a very strong interaction, but very short range. And you can think about it as just like the atoms behaving like marble balls or billiard balls, and they just sort of like bump off each other when they get close to each other, but otherwise they don't really interact. And this is nice because this is something that we can tune via changing a magnetic field, and you can make your billiard balls repulsive, which is how billiard balls work, but also you can make them attractive, so they can make them attract each other. And then the other kind of interactions that we have in our system is just dipole-dipole interactions, which is a bit like how bar magnets behave. And this is interesting because this is long range as opposed to the contact interactions. So the billiard balls don't interact with each other if they are far away, but magnets do. So that's great. And then the other thing is that it has a directional dependence. So if you put sort of like two bar magnets next to each other, then they will repel each other. But if they are sort of like below each other, then they will be attracting each other. So what that means is that you add another term to your interactions, and that means that you just basically you're able to discover more depth and depth of physics in that sense. So there are lots of dipolar atoms, well, not lots, but there are a couple of dipolar atoms which were made into Bose-Einstein condensate: chromium, dysprosium, and erbium. And you can do lots of different things with these. You can look at how they collapse, and you see this like very nice sort of like clover leaf-like pattern, which is very interesting. Also, you can make them into droplets. You can look into super solidity, which means that it's sort of like it crystallizes in the sense that it gets density modulated, but it still sort of like flows frictionlessly as a superfluid would do. And you can look at its excitation spectrum and all that. So then thinking about the Oxford erbium experiment and what we do here in Oxford this is how our experiment actually looks like. And then later on, I'm going to be talking about what then we actually do with this. So this is how our experiment actually looks like. So this is sort of like a large vacuum chamber that you see here with lots of different sort of bits and blobs. And the first sort of most important thing, or like the first thing to say is that we have an oven of erbium, which is just an element like oxygen and nitrogen. So we have an oven of erbium, and we actually need to first heat up things before we cool them down. And the reason is because erbium is just a metal as I don't know, iron. So if you want to make erbium into this very, very cold gas, well, you first need to get a gas. So what you need to do is that you need to heat up erbium to make it into a gas, so to have some vapor pressure, and then you can cool that down. So we actually heat up erbium to quite a bit, to more than 1,000 degrees, and then the erbiums from this place just sort of like fly to the left, okay, down into this chamber. Okay, so the erbiums are coming from this oven and they fly into this way. And we first apply transversal cooling. So what we say is that, okay, you have this sort of hole on your erbium oven chamber, but then the erbium just sort of like comes out like this, and you want to make it collimated so that it actually goes down your tube, and you basically sort of compress it by cooling it in the transverse directions. Okay. And then the next thing that we have is something called the Zeeman-Slover, which uses exactly that laser cooling technique as well as the transversal cooling. It uses the exact laser cooling technique that I mentioned, that we just, the atoms are sort of going down to the chamber from the right to the left. And then there is some laser light coming in from here and then going on to the right. So the atoms are counter-propagating a laser beam. And it's called the Zeeman-Slover because what you see around this, what you see wrapped around this tube is a series of magnets, coils. Because if you think about it, well, okay, we said that like there is this Doppler shift involved in cooling the atoms, and this is something which is very important later on. But you know, as you slow your atoms down, well, obviously they get Doppler shifted away. So to counteract the Doppler shift of the atoms slowing down, you change their energy levels by changing the magnetic field. So using the Zeeman effect, essentially, and that's why it's called the Zeeman slower. Okay, so the atoms are now slow after exiting your Zeeman slower here. And then what we do is we put them into a magneto-optical trap. So that stands for MOT. And you have these 6 beams going from, you know, plus minus X, plus minus Y, plus minus Z, so all the different directions. And this way you can trap them with also a magnetic field present, and then you can trap them and cool them down to sort of like these tens of microkelvins regime. Okay, finally, what we can do is then we need to transport the atoms into something called the science cell, which is just basically a glass cell. And the reason for transporting the atoms here is that, okay, well, this is a big vacuum chamber, which is good for vacuum, but it's hard for optical access. So we have a small glass cell as well attached to it, which is also under vacuum, of course, but it just grants you a bigger optical access. So that's better for your experiment. And then you can use the evaporative cooling there, and you can sort of evaporate there and go and condense your stuff into a BEC after you've transported them. All right, and so when you actually put your atoms in the science cell, this is how we then finally trap them. That's how we plan to trap them, I should say. Is that we have a 1030 nanometer laser, and that's the optical dipole trap that I explained earlier. So that sort of like traps our atoms in this direction, in this along this axis. But then we also have a sort of like a blue detuned tube. So this is an anti-optical dipole trap in the sense that it does not trap atoms, it repels atoms. So that means that, okay, your atoms are trapped in the middle, and then you sort of like have a rim around them and you won't let them escape. So they are trapped in a sort of like a disc-like fashion, as in like a pancakes trap, essentially. So that's how the experiment looks like. In a simulation in real life, I should say that it looks more like this. So, you know, on one table you have lots of lasers and optics and whatnot for shifting your light frequencies to the right frequency and sort of like generally controlling your light passes. But also on the other table you have the vacuum chamber that I've just described in the previously. And if you look into the vacuum chamber, this is how a MOT looks like. So you see that there is this sort of glowing thing in the middle. So this is just a viewport on the vacuum chamber, and this is sort of like 1 inch wide. So what you see in the middle is like, you know, a good centimeter or 1.5 centimeter, and this is, well, quite cold atoms. I wouldn't necessarily say ultra-cold atoms, but this is sort of like tens of microkelvins, and you can literally see them. So that's something which is quite nice. All right, okay. So this is how our experiment works, and then what we can do with them, and this is sort of the last bit of the talk, is the actual sort of science that we want to explore and can explore with this. But there are multiple things that you want to look at. The first of all is Roton physics, which I'm going to explain in a bit more depth in a minute. The second thing is phase transition dynamics. So this is just think about, as I've said, that the phase of the BEC is something which you want to look at, is something which is interesting to look at. But you know, whether you are able to establish a single phase across your BEC, or you have some like domains with, you know, this domain has such a phase and then another domain has some other phase, depends on how quickly you cool down your atoms. And something which we want to look at is exactly this phase transition dynamics. So, you know, vary the time required to cool the atoms down, and see like how big a domain you form. This can be familiar for magnetism. You know, magnetism, standard magnets have this kind of domain structure. We would also like to look at the effect of long-range interactions on turbulence. So, well, turbulence is now fairly well discovered for only contact interactions, when you only have contact interactions between your atoms. But it is still a way to go to understand how the effects of long-range interactions and magnetic interactions affect turbulence in general. So that's something that we would want to look at. And finally, we also plan to do impurity physics. So our experiment is especially in the sense that we don't only have one type of atom, but we will also have another type of atom. So we won't just have erbium, but we'll also have some potassium in it potentially. And the idea is that to mix the two atoms together and then see, how the potassium atoms as an impurity interact with the erbium atoms, which would be, there en masse, if you like. And this is something which we'd like to explore later on. But focusing on Roton physics, so the idea is to look at how the interaction energy changes, and like how the excitation spectrum of your Bose-Einstein condensation changes, or how is it affected by having the magnetic interactions. And your atoms are trapped in a pancake trap, and they are interacting with each other via dipole-dipole interactions, as I've said. Okay, so this is your atom sort of in the middle, and these arrows are meant to symbolize that their magnetic axis is along this axis. So they are sort of like spread out and like and put in this pancake way, in this pancake trap. And if you think about it, as the condensate is excited, their orientation changes. When I mean excitation, I mean sort of shaking, if you like. So what you can think about it is that, okay, well, if your atoms were in sort of like in a completely still, position, that they would just be in a pancake. But like as you start to sort of like shake it, obviously that means is that you have your atoms sort of like moving around each other in this direction, sort of perpendicular to your pancake. And that means that their interaction energy changes because they are magnets, as I've said. They are like magnets, as I've said. So if you can think about this, is quite a nice figure of like, having having sort of like stronger excitations on your BEC, and you can see that, well, in the lighter excitation scale case, your atoms are sort of next to each other, but if you excite them very much, then they will be sort of like below each other. And what that means is that, okay, you've sort of like increased your excitation, so you would expect that the energy goes up because they are just moving around quicker. So just sort of like in a kinetic energy point of view, just say that like they have a bigger kinetic energy, which is true, but also they have a smaller interaction energy because of the magnetic interaction and the dipole-dipole interaction. So what you can say is that, okay, well, as I increase my interactions, my magnetic interactions, I can sort of go from sort of like this way, sort of like engineer a dip, if you like. And also, if you increase your magnetic interactions far away, then you can actually make this interaction energy go to zero, or excitation energy go to zero at some finite momentum. And this is the way the supersolidity gets engineered. Actually, you can think about it that basically what happens is that you just basically find another ground state of your quantum system where it has a finite momentum, as in like it's basically density modulated, and it's happy to stay at that stage. And why is it, or like how does it affect all the other phenomenon? Is basically one of the things that you can read off, or you can calculate from your excitation spectrum, is the critical velocity. The critical velocity is basically a concept related to superfluidity. So, as I said, these Bose-Einstein condensates are like a superfluid, which means that they under some critical temperature, critical velocity, they flow frictionlessly. That means there is absolutely no viscosity in your system, a bit like in liquid helium. And if you change your interactions, you can change that critical velocity. So, if you stir your BEC below that critical velocity, that means that you can stir it, but you will not heat it up because there is no energy dissipation. There is just no energy dissipation in your system. Whereas if you stir it fast enough, then you will actually sort of like enter into the regime, but you actually will be able to disperse some energy in your system. And the critical velocity changes because the critical velocity can be well calculated by having a tangent line from the zero to the minimum of your energy scale. And as you increase the interaction energy, this dip goes lower. So that means that your critical velocity goes smaller. Essentially, this is something which we would like to look at. All right. So as a summary, and this is my final slide, just to give a summary about what I was talking about. So I was talking about that in these ultra-cold atoms, we cool atoms down to sort of like a 100 nanokelvin regime above absolute zero. This is good because we can access various quantum physical phenomena. And in Oxford, we do this with an extra twist, as in we have dipolar atoms in our case, which is nice because we have an extra interaction. So we also have dipole-dipole interactions besides our contact interactions, as we would like to use first of all to study Roton physics of erbium atoms, but then there is also the other possibilities, as I've mentioned. Last round is acknowledgements. I very much thanks my colleagues and our sponsors, and I'm looking forward to taking any questions that you have. Thank you.
Thank you so much. That was really, seriously, that was a really amazing talk. So we now open up to questions. So if you have any questions, unmute yourself. If people are a bit reluctant to get started, then I shall start off with my own question. But all right, I'll start off with my own question. People, seriously ask anything you want, because this is like the perfect space, right? No one's judging. So, you know, you had a slide where you showed like what measurements you could make with the different elements. And
Yes.
one of them was sort of like a like colored, like, yes. Those are spherical harmonics in the bottom left corner, right? Are those like because those look like the wave functions of the electrons, but how on earth could you see that?
Yes, it's I would say it's completely unrelated. That is, it's in a similar shape, yes, but it is a completely unrelated thing. So what it says here is D wave collapse, and I haven't quite explained what that means. So if you have only contact interactions, you only have an S wave collapse, which is like the S in your wave functions. You know, in your wave functions you have like S and D and all these kinds of states. So an S wave is something which is completely symmetric, and if in the contact interactions case, your contact interactions are completely symmetric. So if you have your atoms, and then you sort of like make them collapse, as in like you increase their density too high, then basically they collapse in a way that it looks like a sphere. Okay, so that's like an S wave collapse. Whereas a D wave collapse, contrary to that, is if you have dipolar interactions. So that just means that you have this sort of like second spherical harmonic, as you say, because this is dominated by the this is dominated by the dipolar interactions and the dipolar nature of those interactions, and not the contact interactions.
Okay.
But it has absolutely nothing to do with how the wave functions are like. It just happens to be the same geometry.
Oh, okay. It's just.
But it was well spotted, yes, and it's
just because there's a reason why it's called the D. It kind of. I was what? But yeah. Oh, that's really cool. Okay, so we have a question in the chat. Is optical trapping always better than magnetic trapping?
It is different, but it is also well, I should say it's better in the sense that, as I've said, that in this magneto-optical trap, there is this limit that I was talking about, this Doppler limit of the cooling. So let me just go back to that slide very quickly. This bit here, okay. So if you put your atoms in a magneto-optical trap, then you cannot make them colder than the energy associated with the recoil of a single photon. So you think about, you know, having an atom completely still, just for the sake of a thought experiment, and when it absorbs a single photon, you know, it will be kicked by that photon, and then it will like emit it in a random direction. So you cannot have it sort of like, you cannot have it stationary, as in like arbitrary cold, because of this recoil essentially. Whereas in optical trapping, you use a very different kind of trapping. You basically use this sort of like this process here, whereas okay, the atoms are confined to this space. At this point, you don't slow them anymore, actually. So this is you know, you can think about confining stuff in two spaces. You can either slow things, or you can make them sort of like physically confined. And that's two different things. Okay, so you can like make them, for example, in the previous case, you slow things down, but that does not mean that you confine them in space. So that's the reason why we actually have a magneto-optical trap and not a purely optical trap, in the sense that it's not just the beams are there to slow the atoms. It's the magnetic field along with the beams which does the physical trapping. Whereas in this case, the beam does not slow your atoms anymore. It's just there to create a potential. If you see it in this slide here, it says all the wavelengths. Okay, so we use 401 nanometer and 583 nanometer to slow the atoms down, but we use 1030 to trap them. So the atoms do not absorb this light at all. It's just used to trap them physically. So I wouldn't say that one is superior to the other, but I would say that, this way you can trap them, and if you lower your trap, you make the fastest one escape, and that's how you sort of like cool them with the evaporative cooling thing. But it's just a different thing. This is much less useful for high temperatures, and that's why we not only have this, for example, is because, well, this is not very efficient. You can get to arbitrary cold, and that's good, but it's not very efficient. So in the process of cooling atoms down, if you start off with, say, 100 million atoms and then you go to 1 million, you're not bad. That's good. So you only lost your 99% of your atoms, and that's an acceptable result. That's fine. Yeah, but this is the sort of conversion ratio one should think about. Yeah.
Awesome. Got to thank you for that question. Does anybody else have? Okay, what time does it take for atoms to go through the Oxford ER setup?
Good question. It's actually not that quick and not that slow either. So sort of like one experimental run, if you like, is, well, at the moment, it's about sort of 30 seconds. The way we are, the current stage is that we have atoms loaded into the magneto-optical dipole trap, the magneto-optical trap in here, and we are transferring them to the optical dipole trap so that we can actually move them down to the science cell. Okay, so like up to this point, when you load the atoms into your magneto-optical trap, and also you let your coils cool down and whatnot between experimental runs, it's say 30 seconds. So like you could produce a mod every 30 seconds if you like. From there, evaporation could be another tens of seconds or so. So this sort of like the altogether, this could take a minute or two, I would say. Yeah. So that's how often you can produce a BEC. That's basically a repetition rate that you can sort of like take images at, or like that you can produce BECs at. Atoms fly them very quickly, but they fly them so quickly that some of them are just sort of like going straight down this way, and they're not even trapped in the magneto-optical trap. So the reason that you need to keep it that long for like 15 seconds is not because it takes 15 seconds for the atoms to go down. It's because you don't trap all the atoms that actually reach this point. So you need 15 seconds to achieve a high enough atom number, which is good enough for evaporation, because as I said, evaporation is very very lossy. Yeah. So I think you're muted.
Yeah. So if anybody has any more questions.
So the Bose-Einstein condensates are something. Oh, I should have a look at this. Bose-Einstein condensates are something which, like, we've heard about in the second year thermodynamics course, but for the most part, there we assume that they don't have any interactions. So I think for me, like, talking about what happens when we have dipole interactions was quite interesting. Are there any other types of interactions that we can look at in Bose-Einstein condensates, which would maybe decay on a different scale or something like this?
I would say that it's not something that I could say from the top of my head, and it's but I would say that it's not something that I know about, but it does not. I'm not saying that it's absolutely not possible. I mean, quite possibly, maybe you can engineer something just with your light, but it's not something that I know from off the top of my head. It's part of the reason why everyone looked at contact interactions, and there are so many things to explore as well. So contact interactions are not sort of done, if you like, and there are a couple experiments in the world, say, I don't know, up to 5 or 10 or whatever, which look at dipolar atoms, but not that many. Yeah.
Awesome.
Talking about just one more thing about interactions is, I'm not sure if you've learned about this then in thermodynamics, but I think one of the standard examples is that can you make a Bose-Einstein condensate in 2D? And the answer is no. So how can we actually make a Bose-Einstein condensate in 2D then? Because this is all like, pretty 2D. Like it's 2D enough in the sense that it's like atoms are next to each other. So like as 2D as you can get. And the answer is precisely interactions. So in the non-interacting case, you couldn't make a BEC, and that's a standard bookwork example. But if you have interactions, you actually can. Yeah.
That's really cool. We have another question from the chat. Does this approach, by continuing to increase the sizes of the Bose-Einstein condensates, provide a path for investigating gravity quantum interactions, or do we run into unsurpassable experimental limits?
Yeah, that's a very, very good question, and that's actually the reason for one of the motivations that you can do with this is precisely to look at gravitational effects. So actually, it was, I think, just maybe half a year ago or so that the first time on the International Space Station a BEC experiment was launched, and that's partly to figure out what's the role of gravity in all this and like how the BECs work in a non-gravity environment. So the answer is yes, in that sense, that you can make them, you want to make them big enough, but also there are losses. So like there is only so many atoms that you can trap in your magneto-optical trap. There is only so many atoms you can convert into a BEC. So it is, at the moment, you cannot go to an arbitrary large atom number. I can't tell what's the largest ever BEC created, but I'm sure it can't be more than a couple tens of or hundreds of millions for sure. So so there is this sort of like practical limit. But I mean, as science advances, it took 70 years to come up with a BEC in the first place. So we'll see.
Awesome. Okay, another question from the chat. How do you stir or rotate the condensate in the vortex experiments?
That is a very good question. There are actually multiple ways to do that. So one of the things that you can do is to use exactly a blue detuned laser beam. So when I say blue detuned or red detuned, I mean it with respect to the atomic transition that we are talking about. So in the optical dipole trap case, if you have something red detuned, that means that your atoms will be attracted to the laser beam. Whereas if you have something blue detuned, that means that they will be repelled from the laser beam. So, the way we trap atoms is that we have a red detuned sheet, so they stay in the sheet, and then have blue detuned walls, so they are in a pancake. And then how can we stir them? Answering the question is, well, okay, so let's just have another blue detuned beam, just as like a single beam going through like this, along the horizontal, along the vertical axis. And if you have that blue detuned beam and sort of like, you rotate it around your BEC, you basically stir it as if you had like a rod, if you like, and you would like stir it essentially. So that's one way to do it. Another way to do it is to rotate your trap, for example. Not in our experiment, but in another experiment, the atoms could be trapped with a magnetic field, and you could rotate your magnetic field around, for example, and that would mean that you start sort of like rotating your BEC as well. So these are the two ways I know of. Yeah.
Awesome. Another question from the chat. Great, keep them coming. What is the form of the dipole-dipole interaction in the Hamiltonian? Is it more than a Heisenberg interaction?
What does he mean by Heisenberg interaction?
I am not sure.
Okay, me neither, but I would say that we model the interactions in a completely classical way. We literally use the same equation that you would use for two bar magnets, in the sense that we assume that the atoms have an intrinsic dipole moment, and you have like dipoles next to each other, if you like, and they interact in a classical way, if you like. So we don't assume anything more to this. Yeah.
Cool. And yeah, I don't know if people have any more questions. Okay, some sort of grad type questions. So somebody's asked, which part of this research do you enjoy the most?
That's a good question. To be honest, I quite frankly enjoy being in the lab. I mean, to be honest, this just looks cool to me. there are multiple things. Experimental research is nice when it works, and it's a hassle when it doesn't. And I would say that it's 80% not working. That's just like how experiments are being run. But just the other day, I think it was literally yesterday, I was thinking about actually putting it into this talk because of this online format. I didn't want it to. We've just taken a video of like basically a mod growing, and then like how we actually sort of like compress it. So before we actually transfer this mod, so like these trapped atoms into an optical dipole trap, we first actually need to compress them into something smaller, so they can have a better overlap with your optical dipole trap laser beam. So literally yesterday we took a video when you see that like, okay, you run your experiment, and then you see that like this blob, if you like, gets just bigger and bigger over those like 15 seconds as you collect more and more atoms. And then you can like sort of see them like compressing and then just disappearing. And that the sort of compression takes place over half a second or so. So you can still sort of like see it with your own eye. That was, such a joy for me. We measured the temperature, and we got about 30 microkelvins. Have you seen something 30 microkelvin cold above absolute zero? I haven't so far. It's really amazing. All these lasers are very colorful, except mine. The one which I'm working on is the 1030, which you can't see. So, everyone has these nice shiny lasers except mine. But yes, so I enjoyed that part of the most, just being in the lab and working on something which I think, frankly, is just really amazing and really interesting. For me, looking at, I'm a bit like St. Thomas in the sense that, I don't believe what I don't see. And quantum physics is especially hard to believe for, I think, many people, and also for me. But, when you see this experimental evidence of like matter wave interference, as I've showed it in another slide, I mean, this is just, like really interesting. You have something which, are atoms, that there are atoms there, these are like two things, and just like let them fly away, and you suddenly see these waves as if they were like waves. I mean, that's just really amazing. Yeah.
Oh, that's so cool. It's really nice to see somebody like so enthusiastic. So often people are like, oh, no, but yeah, physics is great. We know this. So we have another question from the chat. It says, I'd like to tackle a quite recent achievement into Bose-Einstein condensate research. In June, a Sussex researcher, Dr. Amrita Gaj, succeeded in conducting the first remotely created Bose-Einstein condensate experiment. Could you tell us more about the actual implications regarding quantum computing and other practical usage like sensors?
Sorry, I didn't get the first part of the question because the internet was going a bit.
You can see it on the chat if you want.
Let me try to open it. I see participants. I'm not sure if I see the chat, to be honest. I do. Yeah. I do actually.
It's not the most recent question, but it's the one above that.
Okay, so yes, I'd like to tackle a quiet. Okay. First, you made the great BC. Yes. I would talk about the impurity side of things to talk about quantum computing. So I've mentioned that. Actually, let's just go to this slide here about the Oxford experiments. One of the details I skipped over a little bit is this. So as I've said that, okay, we'll have two types of atoms. So there will be, okay, so the erbium comes from here, and this is what we have currently, but we'll also have this extra source of potassium atoms. Okay, it stands for potassium, 2D plus rather than a 3D mod. Okay, so there will be an extra potassium mod here, and the potassium will fly from here down into the chamber and then onwards to the science cell. Okay, that's the idea. And then you will have an erbium bath and like a potassium impurity in it. And it's what we want to look at, and that has an implication for quantum computing, is we want to engineer something called a non-Markovian reservoir. Okay, this sounds very involved, but what that means is that normally your environment works as a Markovian reservoir, which just means that you couple to lots of different energy states of your environment, and that means that you just have a quantum system, and then because of decoherence you lose information. Okay, and information just goes away, and it's just information is lost to the environment over time. That's one of the hard things about quantum computing, because you cannot have your quantum bits forever because of this decoherence over time. And that has to do with the excitation spectrum of your background or your surroundings. Because you have a large enough surroundings, you have a continuous excitation spectrum, and then you continuously excite all the different energy scales, and so you have lots of different frequencies associated with those energy scales, and the whole thing just goes into a mess. However, if you have dipolar interactions, as with our erbium atoms, you remember that there was that dip in the interaction energy towards the very end, which I was talking about. So this dip sort of here. What that means is that you don't continuously excite all your different momentum states, but you only excite, well, those which are very small, but also this one, because this is also very small. Okay, so you have like a finite energy, and you don't excite everything, but you excite sort of like this bit here and this bit here. So that means that, well, you don't lose your information and your coherence sort of over time constantly, but rather than you have a beat. It's what that you basically excite this bit here, but this is, you know, some wavelength. It's not like complete gibberish and just noise. It has a wavelength, it has a time constant, and that means that, you know, essentially sort of like pump information into the environment, but then, you know, the information from the environment goes back into your qubit, if you like. And that's something which is called a non-Markovian reservoir. So that is a direct implication to quantum computing, as something which we'd like to explore, whether we can actually, you know, make the decoherence times much longer by engineering a background such that it actually, you know, it's not just that information is dissipating into the environment, but it's okay, it's a periodically pumped back into your quantum bit. I'm not sure if this was understandable. If not, I'm very happy to talk about this in more detail. So just ask. Yeah.
Great. We got a nice thank you message on the chat. Thank you. Yeah, we like organizing these events too. I think Amanda and I and like the committee, we always like to ask, especially since you're a grad student. So what kind of got you into this field, and sort of what sort of things would you recommend for people who are interested maybe in getting into it?
Yes, in my field, or into like being a graduate student in physics generally, or
into your field more specifically.
Yes, it was an interesting decision to make. You know, I was a fourth year physicist, and I felt that, you know, frankly, there are just so many interesting things in physics. I was just very excited in general, and you know, there are lots of nice things to look in the sky, and you know, you see all these like nice pictures of galaxies. If you want something more applied, you can go to condensed matter, and then you can work on, I don't know, high temperature superconductivity if you like, or whatever. And frankly, there's just so many interesting things to do. So the way I ended up with ultracold atoms is precisely because of this attitude that I don't like not understanding something, and I don't believe something I don't see. And I feel that we don't really understand quantum physics, if you like, in the sense that we can calculate it. There are lots of concepts flying around, but frankly, how can be something like a particle and a wave at the same time? I mean, it's just crazy. Like, this is not something that you can imagine. And maybe, you know, the world is just fundamentally different, and that energy scales and you know, it's something that we cannot imagine because it is different. But I wanted to, you know, explore this in a bit more depth, and I did a third-year project on something called the quantum Zeno effect, which is about if you observe a quantum system, it would not evolve. And one of the questions raised in the field is okay, is a null measurement a measurement? Is it a measurement when you don't see something happening? And, you know, these are sort of like borderline philosophical questions, but this is still tackled from a very physical point of view. You can sort of like make experiments with negative results, but you don't see something happening. I don't know, you don't see your atom decaying, for example. And was this a measurement or not? So these are, I think, very interesting questions, and I would just be interested in sort of like exploring in a bit more. And that's what led me to this field, and that's what led me to ultracold atoms. There are very interesting things to look at. A few things that I've described were quite, I wouldn't say applied to my taste, but like, you know, still sort of high level in some sense. But you know, just generally trapping atoms, for example, in ion traps, which is a little bit different to what we do, but you know, it still involves atoms and trapping. There are groups looking at, you know, is hydrogen and anti-hydrogen the same in the sense that do they have the same absorption spectrum, for example? And I think these questions are very fundamental questions, are very interesting questions. There are lots of groups looking at, are the physical constants changing? I mean, we assume that, you know, the speed of light is a constant. We assume that the Planck constant is a constant, like we even call it a Planck constant. But is it actually a constant, or is it actually changing in time? I mean, and if so, then how much or why? So these are very interesting things to look at. How to get into this field? Well, I would recommend taking atomic and laser physics in third year, and like in fourth year, sort of like specializing towards this. In my fourth year, I did well, atomic and laser physics partly, and also particle physics. I wasn't quite sure whether I want to work at very low or very high energies. And the other thing I would wholeheartedly recommend is, you know, try to do a summer project with one of the groups. Just, you know, reach out to the people working there, the people running the group, and ask if they have anything for you to do. I mean, usually they would be happy to take on students.
Yeah, that's really interesting. Yeah, and I would definitely, from my experience, recommend, if people are interested in research, to do the summer projects, because usually researchers are really happy that somebody gets in contact with them. I don't know what your experience is, but like, you know, it's nice to have keen undergraduate students. Yeah, that's really interesting. Okay, we have another question. So somebody has a question about experimental physics. They say, how do you cope with all the stress when things just don't go straight?
Okay, so as I've said, I mean, things usually don't go straight, and the whole, I think, frankly, I mean, like a large part of experimental physics is figuring out how to do things, and you know, one of the and this can sometimes take, you know, a very long time. So just going back to this slide here, I mean, these guys got their Nobel Prize in figuring out how to cool atoms, as well as this guy here. Okay. They literally got their Nobel Prize for this, but also, like, just back, I think, even more a bit, these three people got their Nobel Prize for making a bees. It's this like very experimental research. It was not, you know, the theory was worked out 70 years earlier, literally, for the BEC at least. The cooling was theoretical work as well, of course, but this was very experimental work. So coping with the stress, I mean, like, as long as you have a clear objective of what you like to do and what would you like to see, and you set realistic targets, which research groups frankly normally do, because otherwise they don't get funding, things will work out eventually. It's just there is some time which will take you to get there, but they will work out eventually.
Yeah. Oh, awesome. So again, if people have more questions, I mean, you can always send them to the Physics Society email address, which is on our website. I presume people know our website, or our Facebook group. Hang on. Somebody has a question. What do you think is the most critical skill for being a successful researcher?
Ooh, well, that's a hard one. I mean, resilience, for sure, especially in experimental physics. As much as I've said that things work out eventually, you have to believe that it's actually true. So you have to keep yourself motivated for years, and to be able to do that is very important. I would also emphasize two other things, and one is creativity. You know, you have to do, if you want to be a good researcher and you want to succeed as a researcher, you have to be creative and original. Even though you have to sort of like stay on the ground with 2 feet, and, you know, you have to know what you're doing, but you have to be original and creative. So that is actually important. You also need to have a lot of knowledge to back up what you're saying or what you think, but that still means that you need to be creative. And the other thing which is interesting, and not many people think about this, but it's something which I saw in lots of different cases, is communication skills is actually quite important. Part of the reason for this, especially in experimental physics, is because normally you run an experiment with multiple people. So in my group, there are, as I've shown in the last slide, currently we have 3 PhD students, including me, the postdoc and the PI. So there is 5 people, plus the master students. This year we'll have 2 master students, and plus we occasionally have some students. So you have to know how to run a group, in a sense that you have to be able to get on with people and motivate them, the people you get who are under you, but also, you know, science communication, in the sense that, like, communicating what you do towards scientific audience, to be able to convince them that this is, you know, the way to go and this is actually exciting and these sort of things. These are, I think, in my opinion, these are a little bit underrated in the scientific community, but I feel that most of the people, I would say actually all the people who I've met and got like Nobel Prizes or were sort of like close to that level were very normal people, in the sense that they were not the archetype of the scientist that you imagine, you know, being, you know, very self-involved and not very outward looking. They were very nice people and very capable and just very good, obviously very smart.